A especially difficult case when it comes to studying titration is the titration of polyprotic acids. A polyprotic acid is an acid that can give more than one proton. In any case, it will give one proton at a time, but if you keep adding base to the polyprotic acid, you will still see more than one equivalence point. In this case, for example, we are going to see the the titration curve of phosphoric acid. As you can see, phosphoric acid has 3 protons to give. So let's see what shape would it have if I draw the titration curve of phosphoric acid. Phosphoric acid is a species found in Coke drinks, for example. So it's a typical lab exercise to titrate the phosphoric acid in a Coke drink. So what I'm saying that is it's not that uncommon. So the overall approach is that you can treat a polyprotic acid as if they were 3 different acids that you have in solution. First, the most acidic will react, then the second most acidic, and finally the third most acidic. So let's see what shape should it have. Notice that we have 10 milliliters, 0.1 molar of phosphoric acid, and we are titrating with 0.1 molar sodium hydroxide. So the first equivalence point will take place at 10 milliliters of sodium hydroxide. You will have a second equivalence point, so 10 plus 10 should be 20 milliliters second, and finally a third equivalence point, 30 milliliters. So let's see. Initially, how do you calculate the pH? Well, phosphoric acid is a weak acid, so you need to use the ice table, and you'll have something like that. What you know is that halfway of your titration, this will be equal to the first pKa, which is 2.148. Okay, that will be pK1. Let me just draw it here. So if this is 7, this is 14, the second pKa will be here, 7.198, and finally the last one should be 12. Just gonna put it because okay, these are halfways of the titration. Okay, so that I know where, not the jumps, but the 3 different buffers that I can see in the titration. So you first start with having mostly phosphoric acid. Phosphoric acid starts to react until halfway of the titration. What you have here is a 50-50 phosphoric acid and dihydrogen phosphate. This is why the Henderson-Hasselbalch equation tells you that when you have 50-50 equal amounts of acid, the acid and its conjugate base, the pH is equal to the pKa that relates the two. In here you will have then the first equivalence point, so forgive my drawing skills, okay, and in here you'll have the second equivalence point, then you'll have another buffer area, and finally the last one that will be not very remarkable. Notice that I'm not going to get out of scale. This should be 13, so this should be a little lower. It's hard to draw at scale. What's important to know in all this titration curve is to understand, 1, what species exist at each point, and 2, how to calculate the pH. Well, calculating the pH halfway in the buffer area, it's fairly easy, because you know that the pH is equal to pKa. Notice that here what you have is hydrogen phosphate. How can we calculate the pH of this solution? Well, it's a base with respect to phosphoric acid, it's an acid with respect to this one. How do we calculate the pH here? Well, the long way to do this is using the ice table. One should use the ice table. Hydrogen phosphate, dihydrogen phosphate is an acid, so one should be able to use the ice table using the Ka corresponding to the Ka2 corresponding to the acid, but there's a shortcut. One can actually calculate the pH at this point. The pH here is equal to the average of these 2 points. So that's very convenient. So again, the pH at 10 milliliters is equal to the pKa1 plus pKa2 divided by 2. We're not going to show why that is, but it can be shown that that's actually the way to calculate the pH. And so this is 2.148 plus 7198 divided by 2. Okay, whatever that gives. Notice that if we proceed at this pH, you will have in species half of the moles converted into still being the hydrogen phosphate and the other one hydrogen phosphate. Okay, and the equivalence point in here, you will mostly have hydrogen phosphate because all the dihydrogen phosphate has been neutralized. Sorry, I have left this one behind. Okay, how can one calculate the pH here? Well, this is the average between these two. The pH at 20 milliliters is, in this case, is pK2 divided by pK3. So 7.198 plus 12.319 divided by 2. On theory, one should be able to draw the ice table, and notice that if you check on that list of memorization of acids and bases that you need to memorize, this hydrogen phosphate is a base, so you would need to build the Kb and find the concentration of OH negative, and then find the pH for that. This formula is much faster to find out the pH at this point. Okay. All right, and finally, what you have here is half of hydrogen phosphate and half phosphate. Okay, and the pH is equal to 12.39, which is the pK3. Okay, and finally, at this point, what you only have mostly is phosphate. Okay, and what is the pH of a solution of phosphate? Well, you need to use the ice table and Kb. Which Kb? Well, if pKa3 is this much, it means that pKb3, if you will, is 14 minus 12.319. Okay, the Ka will be 10 to the negative pKb. Okay, so to calculate the pH here and pH here, one cannot avoid building the ice table. The other points in between, as you can see, they can be just calculated by using the pKa's of the different species. Okay, so it looks complicated, but if you can understand, first identify the important points, equivalence points, and the halfway of the titration of the equivalence points, that will give you a lot of information. All right, let's practice another one. In this case, we're going to titrate, instead of polyprotic acid, the conjugate base of that polyprotic acid. You have sodium sulfate. Sodium sulfate, of course, can accept 2 protons, right? So this would be 1 to become hydrogen sulfate, but hydrogen sulfate can also accept another proton, and that would be sulfurous acid. Okay, notice that I'm already giving you the pKa's, even though this is a base, because you're plotting pH. What you're going to be seeing halfway of the buffer region is pKa's, not pKb's. All right, so notice that the base and the acid that titrates it is the same concentration. So at 10 milliliters, you will see the first equivalence point, and at 20 milliliters, you'll see the second one. Okay, so let's start. First, notice that we can just assume that halfway of the first titration, the pH will be equal to pKa. So if this is 7, this is 7.172. So halfway of the first titration, this will be equal. Notice that I'm starting from the highest now. Okay, so I will start here. I will have, sorry, this is not very accurate. Okay, and then you have the first Okay, and this halfway 15 should give you the pH. Oops, that was not even straight. Not very straight either, but you get the idea. This is 1.8, this is pKa1, this is pKa2, and finally notice, so you will barely notice the jump because it can now go farther than pH 1. Alright, so sometimes the equivalence point are very tiny. So in here you have sulfite. How can one calculate the pH of the initial solution? Well, one needs to use the Kb and building the ice table. What Kb? Well, this is the pKa, the pKb, it'll be 14 minus 7172, which this is around 6.8 something. Therefore, the Kb is 10 to the 6, negative 6.8. Alright, so you build the ice table using Kb. That will give you OH negative. From OH negative, you can get H3O plus, and that will give you the pH. Quite a complicated step to calculate the pH right at the beginning of your titration. Luckily, in here, what you have is a mixture of sulfite and hydrogen sulfite, and the pH here is equal to the pKa. How can one calculate the other points? Well, in this area we can use the Henderson-Hasselbalch equation, pH, pKa, logarithm of base over acid. The tricky part here may be, well, what pKa are you talking about? Well, the pKa that relates the two species, these two species, the pKa that relates these two species is the 7.17. Okay, and the concentration, the base is the sulfite, and the acid is the hydrogen sulfide. Okay. At the first equivalence point, how can one calculate the pH? Well, the pH here, what you have only is hydrogen sulfide. The pH of this solution is the average of the two pKa's, of these two surrounding pKa, 1.5 plus 7.172 divided by 2. Okay, and in here, again, this is the maximum of the, or the halfway of the titration, the maximum capacity of the buffer. This is pH equal to pKa. What pKa? Well, the lowest, which is 1.8. You have 50-50 hydrogen sulfide and sulfurous acid. Okay, so that point is easy. Again, to calculate this point here, it's a little bit more complicated because what you have only is this. So to calculate the pH here, you need to do the ice table using the Ka. What Ka? The one that is 10 to the negative 1.8. Okay, hopefully this gives you some perspective. As you can see, one can spend a good 30 minutes trying to come up with all of the pHs and all of the numbers, mostly because the beginning and the end of the pH, there's no quick formula to find the pH. Alright, we'll definitely practice more in class, but it's good to get used to how much information we can get without barely making any calculation.